you could just like fill the call stack and then it starts emptying it, right? It's kind of funny. You get like a bunch of stuff that's like unfinished, and then when you finish them, you finish all the previous ones, and then it starts emptying the call stack.
Exactly.
It's pretty funny.
Yeah, that's one of the things you really need to watch out for the recursive problems is if the problem set is too big or the data that you're passing into it is too big, then yeah, you can't use recursion with, or you have to break it down into even like smaller sub problems, that sort of thing. Um, but yeah, we'll get right to it, dude. I don't know if anyone else pops in, then they could join us, but yeah.
Yeah, if we have time, maybe could you try doing a different problem like that's similar to the one that I did, but there's like a slight variation just to make sure that I haven't just memorized the whole thing.
What do you mean?
Yeah, like we did that one that removes duplicates, right?
Mm-hmm.
So there must be some kind of variation of this problem that's like a problem that's simple enough
Hmm.
with linked lists. So I can try to code it and just make sure that I haven't like memorized stuff.
Yeah,
That I
yeah.
actually know what I'm doing.
Yeah, I'd
I don't
say
think
as
it's that
far
hard
as
though.
I'd say as far as this problem goes, we'll go through all the solutions before we move on to another problem, as I was planning. But that's definitely something we were gonna do anyway. So for sure, for sure,
Yeah, because I want to get my hands dirty.
definitely, definitely. Yeah, I'll give you an opportunity if you want to give this code a shot too. You could go ahead and do that if you feel comfortable. I'd say give it a shot anyways, just to try it out. I have the pseudocode here. I'm going to show you a little bit of the diagram right now. So let me just go ahead and share my screen. Get this started. Yeah, I gotta try to be because I'm doing one-on-one coaching now. Like after sessions, trying to start around like 9 o'clock. So I'm trying to be more like have better time management with everything, but it's tough,
Do you
man.
already
Just
have people to do coaching with?
yeah, I had people doing one-on-one coaching for a while, so trying to
Oh,
scale that
I
up
didn't
though.
know that. I thought you were planning that, but I didn't know you already had
Yeah, yeah.
uh, this kind of thing. Okay, Deshaun got it. He's in. He did it.
Cool, cool.
The Mad Lad.
What's up? What's up? All right, so this is the problem we have today. You can see that there's a little bit more data here. We have the same linked list that we were using from the previous days. The first node has the value of 1, second node value of 1, third node value of 2, fourth node value of 3, fifth node value of 3. And so the way that this function works is we're going to have a base case. So you can see the base case up here. If the head or head.next is null, just return head. Because in that case, we just have one. We just have one node, so we'll just return the head. We know we're going to have at least one node. And then this is where it gets interesting and it gets a little challenging because before, with all the iterative solutions, we started with this node and we did some processing on this node. But the way that this function works is right after we check to see if the header is null, then we call the same function, remove duplicates, just with head.next. So when we call, this is like the main function, right? This is call one. We're passing in the head to our main function. When we call it for the first time, we're placing the first function call on the stack. So that's the first function, and we're passing in this head. But then before we do any processing, we're already calling this function again. So we're not, before we even have a chance to do anything, we're calling it again. So we're actually calling this function again, but this time we're passing in head.next. So we're calling this function with this node.
Yeah.
Then same thing. You can see that head or head.next does not equal null. So we keep going. So we actually go to the next line again. Again, it's this function call again. So we're going to call it, but now passing in head.next, which is the third node. So we're calling this function for the third time. Then, same thing, we're checking to see if this or this is null. And since both of them are actually values, then we go ahead, call it again, but this time we're passing in head.next, which is the fourth node. So before we do anything, we're just building up the call stack, and we're calling this recursive function with head.next over and over. And then with call 4, we're calling head.next again. And when we get into this function, this is where things start to get interesting, because now if head or head.next equals null, then we just return head. So on our fourth call, we're on the fifth node. The fifth node is our head. And so we just return the head right here. We don't pass head.next into the function again. We just return right there. And so what we're returning right here is this node right here. And so when we return this call 4 off the stack, this head.next is in the third call. And this head.next is pointing to this node right here, because this node is the one that was returned from the fourth call. And so now we're checking if head.val, because in the third call, this is head and this is head.next, because this one was the one that was returned from this function. And we compare their values. So we're comparing head.val to head.next.val. And if head.val equals head.next.val, then we take our head and we point our head's next variable or next property to head.next.next. So we're actually taking that and we're pointing it to head.next.next. So we're actually skipping this now. We're still in the third call, but we just set head.next equals head.next.next, so pointing it to null, and then we are returning head. So in this case, this is now our head, right? So we're still in call number 3, but we're returning from function call number 3, and we're returning this is the head. So we're going to return from this. Now we're back with this is the head, and this is head.next, because we're returning from call number 3 with this right here. Head.next was set to our node number 4. We're in call number 2 now. So this is our head, and we compare if head.val equals head.val.next, then we set head.next to head.next.next, which would be null, but the values are actually different.
Yeah.
So we just return head. So we're actually returning this is our head from call number 2. So we're taking call number 2 off the call stack. We're back in our first function call right here. This is our head. This is our head.next. We're comparing this head.next equals or head val equal head.next. No, it doesn't. 1 is 1, 1 is 2. Exactly. So we just return head. We're returning this head to our first function call. Now we're back in the first call. This is our head. This is our head.next. We do the check. We see that head.val is equal to head.next.val. And so we point head.next to head.next.next. And then we have nothing left. We're in our last function call, and we just return head. So we're returning this head right here. This head is pointed to this node. This one is pointing to this one, and this one is pointing to null. And the garbage collection will delete these.
Just one thing. What about the node in call 2? There's an arrow pointed to the node in call 3. That's not accurate, is it?
Well, this one is still pointing to this node. Yeah, so you could have 2 different data structures pointing to the same data structure. So you have this node and this node both pointing to this data structure. The thing is with the code that we write, like the program that we're running, if it detects that you're never going to be able to access this node again, that's what the garbage collection is going to go ahead and just
Oh,
delete this. But since we could actually still target this with the head variable in our first function call, it won't delete that. So this will be
yeah,
garbage collected.
yeah,
Yeah,
okay.
this would be garbage collected as well.
What's with the hexadecimal numbers under the nodes?
I was gonna go into like drawing it out in memory, but I decided I didn't want to complicate things if it made sense. But
Okay.
these are just basically this is what a memory address looks like, basically.
Okay.
Yeah.
You're not gonna do it in C++, are you?
It's still a memory address no matter what language it is because these are just nodes that are stored in memory. And so like this node is stored, let's just say for example, in this spot in the memory, and this one is stored in this one in the memory. So when I say um, like head dot next equals this, what I'm really saying is head dot node equals this. Like it's pointing,
Mhm.
it's a reference to this location in the
Yeah.
memory. And
Yeah.
so it's changing its pointer from this location in the memory to now point at this location in the memory. So this location in the memory is just like, it's just going to be garbage collected on the next one, and we're changing the pointer to a different location in the memory, basically. Does that all make sense? Do you have any questions?
Yeah, I mean, it's obviously way more complicated to visualize than the iterative solution because, of course, the iterative solution is way more linear in
Mm-hmm.
the way you think
Mm-hmm.
about it. With this one, you have to go all the way and then kind of, come back one by one and then do what you have to do. So it's not as beginner friendly, but it's the same principle pretty
Mm-hmm.
much.
Mm-hmm. Yep. Yep. Exactly. Do you? We have T and Deshaun. Do you guys have any questions on this here?
So like the way that I sort of seen it or am understanding it is more like a 3D model where I'm putting um I'm putting two 3D squares or like one, two, three, four, five cubes together. Like I'm picturing in my mind like how each corner is connected to a corner that is connected to another square, but it is like known that that corner is connected to that square of that other square's corner, if that makes sense. And then like you could just map it together in some sort of like consistent, like this will never fail kind of thing because this is done using like code, if that makes sense.
The square, you said.
Like so like take like cubes, right?
Mm-hmm.
Like take like imagine a cube, imagine five of the cubes, and then
Mm-hmm.
like having all five of the cubes together, like imagining like it being like three-dimensional. Like how can I can draw it, but like just it's kind of like connecting the corners, like having all the cubes in one space, but having all the corners connecting to each other in a specific way, kind of like a roadmap, where it's like you go from location A to location B to location C, but the way to go back to B from C is from another corner, but then having to map it out in that kind of way, like there,
Um,
yeah.
T, just make sure are you trying to uh tell like how the structure functions like the linked list is?
Yeah, it seems like
Yeah,
that's kind of how
I,
that
I have I might have a metaphor that might be good for you to understand. Like imagine you have a treasure hunt. You have to find a treasure, right? So you find a box, and inside the box there's like some amount of money, like for example, $1, but it also has the address of the next box which you have to look for. So you get the address and you find the second box, or the second box. When you find the second box, there's like maybe $1 or $2, whatever, and then there's like another address showing whether the third box is, and you do that until you find the final box, right? And then after the final box, you just have the value, the like, in this case, it will be like, let's say $3, but you don't have any message telling you where to find another box. Like this is the last one, right? So that this is maybe a good way of thinking about linked lists, like a treasure hunt, where you find boxes, and each box gives you an address to the next box, which in this case would be the next property, right? And think of the dollar amount as like the value that you find inside the box. Maybe that might help visualize it a little bit more.
Yeah, so I'm gonna give you just a little bit of like computer science knowledge right here. I wasn't gonna jump into it, but just to really make it clear, because you made it sound like they might be attached or sequential or next to each other or something of that nature. So when we have like, before we do any of this editing, like when this node is still pointing to this node, when this node is still pointing to this node, before we make any modifications, basically we have this node here. It's the 030 node right here. It's stored here in memory. And we have, let's just say its value is 1, and its next equals, its next is pointing to 5C2. So its next is actually pointed to that right there. So it's pointed to this node here. And then give me 1 second. And then, so I'm not going to draw all these out because it's just kind of complicated with these lines all close. But so we have this node here, value 1, it's stored in this spot in memory. So this node is actually stored in this spot in memory. It has the value property, it has the next property, all stored right here in memory. And the next property is set to 5C2. So it's actually pointing to this location in memory. It just has that, so it's pointing here. What's in this location here is also a node with value 1 and a next property, but this next property is pointed to 5C2. This one's pointed to 1B8, so this one right here is pointed here. So this one right here has the value 2 and its next property as well, but it's pointed to F47, which is like down here. So they don't even have to be next to each other in memory. The operating system is going to optimize like where they put them in memory, and this is like you'll have to dig into like paging or pagination and like scheduling algorithm. Like you'll have to dive into like operating systems if you really want to understand this stuff on a deep level. I think it's like the paging concept. So you have this node here in this spot in memory pointing to 890, so it's pointing to this. So when we do the recursive function and we return from our last call, and this becomes our head and this becomes our head.next, and we're comparing head.val, so this value 3 to head.next.val, this value 3, we're currently pointed to this location in memory as our head in the current function call, and our head.next is 890 in the current function call. But since the values are the same, instead of this one, F47, pointing to 890 in memory, now we actually move this to point to null. So there's actually just a null value in memory that it's pointing to a null value, or it's setting it to like a special object of just null. So it's actually not pointing to anywhere in memory anymore. And then we go back to this, we see that these are the same, or these are different. When we remove one of the function calls and we move backwards, this becomes our head, this becomes our head.next. This val is different than this val, so we just, same thing, move backwards recursively. This becomes our head, this becomes our head.next. They're different, so we move back again recursively. This becomes our head, this becomes our head.next. Now our head in this current function call is pointing to 030, and the 030's next property is pointing to 5C2 in the memory, so it's actually pointing here. But then we do the check. If the head value is equal to the head.next value, then we move the next pointer to not point to 5C2 anymore. It's actually pointing now to 1B8. So now this location in memory that's holding this node, there's no possible way for our program to ever point to this ever again. So on the next rotation, when the operating system scans the memory, it's going to be like, oh, there's no way that anybody can target this node ever again. It's actually going to delete this entirely from the memory. And now this 5C2 actually changed to 1B8. So now this node is pointing to this location in memory.
Jim, that's a great explanation, but it might be overly technical.
Does that make sense at all?
It makes sense. It does, because actually I was gonna show you guys something on my camera because I just drew it.
Okay.
Yeah, because the memory doesn't look like this. I'm just trying to, like, I'm drawing out the memory abstractly so you could kind of see, like, the memory has storage locations for nodes, and this is how you target them, and so,
I follow you.
Yeah, so it's not actually, just because we have our list data structure, it doesn't mean that, like, node 1 is here, node 2 is here, node 3 is here. It doesn't mean that they follow each other sequentially in the memory. The operating system is going to optimize and store them wherever is the best place to store as you're creating the nodes, if that makes sense. But go ahead, you could share.
Yeah. No, I mean, it's because of computers have good memory, right? Like, a computer can never fail you in the memory unless you erase the memory, right? Is that how that goes?
Or there's a bug or something.
Yeah, I'll go ahead and share camera, turn on camera.
Sure.
Okay. Do you see that? Do you see that cube I have on the left side?
Yeah.
Okay, you see that three-dimensional cube? Pretend there's 5 of them. Okay, and then all 5 of them are together on the right side, and then each corner is labeled A, B, C, D, E, F, G, right? And so what you're doing is you're mapping, right? A to D or A to Z or A to J or whatever. But the computer already knows how to map it. Does that make sense? Because of the memory, right? So, like, if you give it like a formula, right? A plus B equals C, then it's gonna go to that spot. It's gonna follow that map, that corner. So, like, from the first cube to the 4th cube, you know, it'll map it out, because you can program the computer to do that, you know, give it a formula and it will do that formula, like, over and over again if it wanted to, like, or it just depends on, like, how you're putting the formula together, right? And then you're then allowing the computer to compute it, to map it. Does that make any sense?
Why are the cubes on top of each other?
No, this is like a kind of like a 3-dimensional thing. You notice how the cube is 3D?
Yeah.
It's not a flat surface. So it's like, if you can imagine all the cubes together, right? They would look like all the ones that are on my right side. Do you see the right side?
Yeah.
So each corner has like A, B, C, D, E, F, right? There's 4 corners in a cube, so A, B, C, D, right? And then another cube has E, F, G, E, F, I don't know, whatever, 4 letters of the alphabet. So say, for example, you want one corner to connect to the other, like, we're like drawing the map, like we're drawing. This should be like a 3D drawing. Like, I can probably do that on a computer if I could do that. I don't know. But like,
sorry, Tiva, but I would like to know, like, are you trying to explain how linked list works, or recursion, or? Yeah,
linked list, like how like the corner of A can go to the corner of J, but, you know, like, I'm not going to draw that in there because it's like somewhere back there somewhere, or around the corner, or like somewhere. But so, like, you would want to draw like a line from A to like J. You know what I mean?
Yeah, you're trying to connect the A node to a J node, you're saying?
Yeah.
Okay.
Like, each corner has a letter. like one corner is called, it's A, and then another corner is B, and C, D. There's like 4 corners in a cube, right?
Mm-hmm.
Or
Yeah.
or maybe there's more. Because I just
There
thought
is
about it.
more. Yeah, there is more.
Yeah.
Yeah, but assuming that like each letter is a node, in the case we're doing here, it's a singly a linked list, so it would only point to one other letter. It wouldn't point to many letters, right?
Yeah.
Or am I wrong, Jim?
Yep.
I mean,
you're
yeah,
right.
like you can program it to do however, like you can program it to do whatever pattern you want it, right? So like, I guess like you mentioned the linked list, it doesn't have to be like, like rigid. Isn't that like what you also said, Jim? Like, it doesn't have to be-
A linked list is gonna only point to one other node. So like one node only has a next property, so it's only gonna point to one other node. But we're gonna get to trees and graphs eventually.
Yeah.
And with those, then you could have like one node, like in a binary search tree, each node will point to 2 different nodes max.
Mm-hmm.
So you have like a left and a right. So that's when it starts getting where you could point to more than one different node. As far as the singly linked list goes, yeah, you're just pointing to one node.
You're way ahead of us. You're a T.
Yeah, you're thinking ahead. Yeah, you're thinking
Which
ahead.
is good.
I like it.
But
Yeah.
it's simpler than what you described the linked list, right? It's way simpler.
Yeah, you're making me think of graphs with the
Yeah.
way that you're describing this. You're making me think of graphs.
But that was a good draw, by the way. It was like,
Yeah.
wow, I can draw that. I cannot do this.
Yeah, thanks for sharing that and trying to articulate everything. That's what's up.
No, no problem. By the way, I'm artistic, but like this is nothing. Like I don't do this kind of art like I do abstract art. So anyway.
Yeah,
Oh,
for
that's
sure.
awesome.
Deshaun, do you have any thoughts on this or questions before we move on and actually code it up? I'll invite everybody to my code editor and give y'all an opportunity to type a few lines of code. It's actually pretty simple. Recursive functions are usually very, very simple. Wrapping your head around the concept is much more difficult than the actual code. There were times when I was like just playing around with code for 30 minutes or 45 minutes and trying to figure out a recursive algorithm, and I always overcomplicated it. I always had like 4 or 5 extra lines of code that I didn't need, and I always ended up narrowing it down to like 2 or 3 lines of code, or like if I had 10 lines, I would narrow it down to like 5. Recursion is way simpler than it seems. Another reason to use recursion, like I told Daniel before we got started, one of the main reasons to use recursion with linked lists and trees is because linked lists and trees are recursive by nature, and so they're going to be much simpler to reason about. Another reason is they are recursive algorithms are easier to prove inductively. So like it's easier to create a mathematical proof that proves your algorithm is working correctly. I'm not too big on math, but I know I work with another guy who does only functional programming, and everything is a function, everything is recursive, and that's kind of hard to wrap your head around, where you're writing a program, like writing a server with only recursive code, but it actually eliminates the number of errors in your code. It's much higher quality code. There are definitely some reasons why you would want to use recursion. So it's definitely something you want to know, especially with linked lists and trees. And so with this problem, we would never use recursion, just so you guys know. Like recursion with this problem, there's so many other good solutions for this problem that recursion is not one that we would use, unless the person in the interview or the person at your company was saying, hey, I don't care about space efficiency, I don't care about time efficiency. The most important thing is readability and simplicity, and I want you to write this algorithm in the fewest lines of code as possible. Then you would use this solution. Besides that, you wouldn't use recursion for this problem here. But let me go ahead and share the link. You can see we're all in the beginner's guide. I'm going to open up the chat. I'm going to post this right here. Go ahead, click this. You'll hop into my code editor, and y'all could give it a shot typing it out. It doesn't look like we're going to be able to get into the second solution today, but what I'm going to do is we'll open it up. As long as we can solve this within like the next 10-15 minutes, we'll open it up for the last 5 minutes just for like questions. We could chat about linked lists, and I'll show you like a sneak peek of what we're going to do tomorrow. And I'm going to challenge y'all to just on your own time solve this solution. I know, Daniel, you were looking for an opportunity to actually solve it on your own. So I'll go ahead and show you how you would do it with a set, why you would use a set to solve this problem. And it's just like the iterative solution, but with a set. So it's basically just doing already what you did, just with a little bit extra space.
Okay.
But
just make sure I can see the live share, but have you opened anything yet?
Yeah.
Because I don't see any files.
Nah, I don't see you in here either. You might have to close out and sign back in.
Yeah, I'm gonna do it again. Okay, now I'm joining. I get it.
There you go.
Hey Jim,
Okay.
do you mind sharing your screen? Because I
Oh,
can't
yeah.
access the Visual Studio Code.
Yeah. There you go.
Thanks.
What's up, John? I just saw you popped in here. This was gonna be a little hard to catch you up on, just because we've been working on linked lists all week, and we're on our third solution for the same problem. The goal of this week was just getting a basic understanding of linked lists. So we started Monday with an iterative solution. We did yesterday also an iterative solution, just with a different approach. For the first solution, we were able to modify the data structure in place and just change it. We didn't need to maintain the original data structure. But yesterday's solution, we actually created a solution where we can create our new linked list while also maintaining the original linked list, because sometimes the requirements of the problem is like, hey, we need you to create a new data structure with this data structure, but we need you to maintain the integrity and the quality and the state of the original data structure.
Are these on YouTube?
Yeah, yesterday's is on YouTube. Tonight's will be on YouTube. And then, yeah, I was just trying to figure out a way to put them on YouTube, and a couple of them are recorded and my voice was messed up, so I figured out what was wrong with that, and they should all be there from now on. And I labeled them as far as like timestamps go, so you could like fast forward and rewind to the important parts.
Okay.
Yeah. Let's see.
Thank you.
Yeah. But Daniel, it was funny because Daniel on Monday, he was like, I'm not ready for linked lists. The last couple of days are already hard. Like they're challenging to wrap your head around. And then like day 2, day 3, he's like, I got it. I solved it on my own. Like it all started making sense and clicking. And it's cool. It's cool because it didn't click for me that quickly with linked lists, man. It took me like weeks to wrap my head, maybe even longer to wrap.
I was able to solve one problem. I don't know about the other ones.
Yeah.
Yeah. But yeah, it was a nice feeling.
I'm sure if you want to catch up on the first solution, John, I'm sure Daniel will catch you up and just break it down for you. It'll reinforce everything he learned too, so you actually learn faster.
Yeah, absolutely.
Okay.
So, all right. So this is the pseudocode right here, Daniel. If you want to give this one a shot here. So basically, what we're doing is this is the recursive approach. So we always have a base case. We are looking for the head or head.next to equal null. When it does, we just return head. Then we call our function recursively, storing the return value of that function call into head.next. Then we check to see if head value is equal to head.next.value. If it is, we set head.next to head.next.next, and then we just return our head.
Okay.
I don't see you in here.
Here.
Oh, there you go. Did you want to give it a shot, or do you want me to write it out?
I can try, I guess.
All right, cool.
Okay, so I guess everybody know. I'm not sure everybody knows, but this is like the class. The class has a constructor. So basically, these constructors have the default values for these properties, which are value and next. Value is like the number that we have stored, and next is the property that points to the other nodes, right? And since this is instantiated, basically you can create objects out of this class. You have to make sure to use this keyword to so it knows that the value is attached to the object. But yeah, that's a bit complicated in my opinion. But
Can I
whatever.
just say? Let me just say that this class definition is a blueprint. That's what it
Yeah,
is. So before you're able to
exactly.
use an object or a class that you created, you need to tell the program what you want it to be structured like. And so this class, this list node, is just an object. It's an object that has two properties. One of the properties is value, one of the properties is next. So every node, list node, is always going to have a value and a next property. If you create a list node, like if you do let new node equals new list node, and you just create one, now there'll be an object stored in this new node variable.
Hmm.
But since I didn't pass anything into the new list node, its default value is 0 and null. So the val property is going to be set to 0. The next property is going to be set to null, and then you have your node. But you can pass in like 5 and new list node. And in this case, then you'd have a new list node. So you'd have basically this blueprint here. Its value property would be 5, and its next property would be actually an entirely new node. So instead of pointing to null, instead of its value being null, it would actually be another node. But this node would have the value of 0 and a next property of null. So you're basically like,
Because you're not passing anything to it. That's why.
yeah. And this node right here, it's just pointing to other nodes. And that node that is pointing to another node. And that node is pointing to another node. So it's just the data structure of a linked list is just one node that points to another node that points to another node until you get to a node that doesn't point to any more nodes. That last node is pointing to null. If that made sense.
Yeah. Yeah, because when you build the last one, you're just gonna have the value. You're not gonna have the anything for the second parameter here. So it's gonna be null by default. But yeah, so okay, so let's try, I guess, to do it.
Yeah,
I'm not sure if I can do it, but I'll try.
you got this.
So if head or head's next property are null, so if head uh is null, or head dot next equals null, then you return head. So what does it mean? Uh, if you so basically, if head is null, it means that there is no node, right? And if head next dot head dot next is null, it means it's not pointing to another node, so it's just one node. So you just return whatever you receive from the argument. Right? Is that correct, Jim?
Yep.
Okay. So
Yeah,
recursive
if you don't
call
have this line of code right here, this code down here is just gonna run forever. So you need a place to catch the last node. That's
yeah.
basically what this is doing. But go ahead.
So recursive call for next node. It's probably I would say it's something like head dot next equals, and then since it's a recursion, you want to call it inside of here also head dot next. So what he tried to say is like we're gonna point like to the next node, but we wanna run a function like recursively. So it keeps checking the next node, the next node, the next node, the next node, like in the call stack, and then we work from the top of the stack to the bottom, like Jim showed in the graphic, right? I don't know if that makes sense, but I hope it does. Because we're not solving like we're not doing like first node and then the second, then the third, and the fourth, and five. We're basically doing like recursively. We calling this, so this one calls this one calls this one calls this, and then this one is called. This gets solved. This gets solved. This gets solved. This gets solved, and then this gets solved, and then we have a result. It's basically the idea.
Exactly.
Okay, so call heads next property.
That's actually
and start
right there.
Okay. Sorry.
No, that's
okay.
good.
So remove duplicate. So to remove a duplicate, we have to check. Let's see. I think it's gotta be a condition, right? If head dot val equals head dot next dot val. So if the, by the way, I think I forgot I forgot a line. I should use current, right?
Nope, no current in this one.
I don't need to do like let current equals head or something like that.
Nope, not in this one. No current.
Oh, okay. So yeah, if the value that we have in the current node is the same as the value that we have in the next node, we need to skip it, right?
Yep.
So what if I remember correctly, you do that by saying that head dot next equals head dot next.
Exactly.
Else, if or else you just move to the other node. So I would say, do I need this else? I'm not even sure I need this else.
Nah, because with recursion, you're never jumping to the next node. You're always just returning the head.
Okay. So yeah, and here it says return the head, which is pretty straightforward, right?
Exactly.
You just return the head.
Exactly.
So hopefully I've done a decent job.
Let's just clean this up to look how nice it actually looks like when you have recursive function, and the reason, so you could actually see the reason why we use recursive function. Like boom, right there. That's just that's just beautiful,
7
right?
lines or something.
Yeah.
8 lines maybe.
Literally like
4 lines.
4 lines of code if you get the space out of there. And if you compare it to like our iterative solution, just, you know, a few extra lines. Our tail pointer, definitely a little extra, you know, but the recursion is just, it's just so clean. It's so nice, man. But yeah, that's yeah.
But
so.
it's ON space complexity, so
Yeah, so it's a little, it's O of n space complexity, O of n time complexity, but it's A+ on readability and simplicity, if you understand, right?
Yeah. Okay, so yeah, this is the solution that I have so far. I don't know if there's anything else to add.
Yeah, no, that looks good. That should actually work. Let's test this bad boy out. Node 3.
Okay, let me check your screen.
1 2 1 2 3, working perfectly. Nice. You got it first try, bro.
Yeah, that's awesome.
Nice. So it's making sense to you then.
Yeah, it is kind of making sense to me.
Cool,
like,
cool.
The thing is, of course, I had your comments there, so I could follow a little better. But I think I could have done it without them. But they were really helpful, of course.
Yeah, for those who it's still you're having a little bit of trouble wrapping your head around this, don't sweat it. I don't think anyone here was here on Monday or Tuesday, and having that Monday and Tuesday knowledge is like crucial for understanding
Yeah.
the recursive solution and understanding this problem or linked lists in general. We really slowed things down. We really went over linked lists and went over the simpler solutions before we came to this one. Tomorrow we're going to go over an even simpler one than this recursion one, so we're kind of going to go back. But I'll give you guys a sneak peek right now before we hop off, just to show you. Let me see if... Yeah, I'll show you the draw.io just so you could get a little visualization of this. We got... iterative simple using set. All right, so basically this is what the linked list is. I showed you the class constructor. So this is a node here, 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 this is a node here. You can see that this first node has a value property and it has a next property. So these nodes, they're just objects in JavaScript. And they have 2 properties each. Every node has 2 properties. Only 2 properties. Not 1, not 3, always 2. So it has a value and it has a next. The value is numerical. The next is either going to be null or it's going to be pointing to another node. So this node, this node, this node, and this node, their next properties are pointing to other nodes. The last node, you could see that it's pointed to null. And so one of the good things about this solution, I think this will make more sense to Daniel than anyone else, just since you've been here all week, is, what is it? Oh, the reason why you would use a set is because this problem that we're doing, this is a sorted list, right? 1, 1, 2, 3, 3. But there are going to be times when you have to remove duplicates and the list isn't sorted. So you're not going to be able to be like, if current.val equals current.next.val, and you could see that they're both 1s, because maybe this will be 5 and the other 1 will be up here next to a 3, so it looks like there's no duplicates. How do you know that there's a 1 here and a 1 here unless you have a set or somewhere to store the values? And so in the beginning of the problem, the first thing you do is you create your set, you create your current, use the head variable to create the current. So the current variable starts as that node right there. You store this value. So you do like set.add, add a 1. And then you do the while loop while current.next exists. When you first get into current.next, you check if current.next.val is inside of this here. Like,
wait, this should be set and not seen, right?
Yeah, it's set, but I just called it seen because
Okay.
these are like the values that have been seen, basically.
Oh, okay. That was a type of car.
Yeah. So yeah, you're checking if current.next.val, if seen set.has current.next.val, so 1, it does already have a 1. It has a 1 from this node here. Then you set current.next to current.next.next. And then you do the same thing. You just go while loop while current.next exists. Current.next does exist, where now current.next is now pointing to this node here. So you check current.next.val. Is 2 inside of the set yet? No, only 1 is in there so far. So you add the value 2 to the set, and then you do current equals current.next. So you're jumping in this node. Then the same thing, you're checking again. Current.next.val, if it's already in the set, then you skip this node, but 3 is not in the set yet. So it's a basic if-else statement. You add 3 to the set, and then you do current equals current.next. So you're moving to this node. Then same thing. If current.next.val, if that value is already in the set, which it is, we just added 3 into the set. And so what we do is we just take current.next and we point it to current.next.next, which is null. And then current.next is null. Break out of the while loop, return head, and you are good to go. Pretty it's like the iterative one. The only difference is There's a little change as far as targeting with current dot next, and then we're adding all of the values to a set as we iterate through the set, just in case. And like I said, this problem is good for if it's not a sorted list, if it's an unsorted
Yeah.
list. And
Because
it's
otherwise you wouldn't want to use it because it seems like it's OM for space, right?
yeah, you wouldn't want to use this solution here unless it was an unsorted. So you know, when you encounter a linked list problem moving forward, hopefully, based on the way that I taught you this week of showing you like 6 different solutions and the reasons why you would use different solutions, like you're gonna be like, oh, is it sorted or not? Oh, it's not sorted. Okay, I can't use the simple iterative solution. I have to use a set. You know, so you kind of like already know what method you're gonna have to use based on this week. And then after this, I'm also gonna show you a solution where you're using a set, but it's a solution. I won't go into the details of it right now, but it's a solution that's good for like if you need to extend your code, or if you need to basically like, so the solution after this one is going to be where you basically iterate over this, storing all of the values that aren't in the set to the set, and then you create a brand new list. So you're able to maintain the original one, you're able to build a brand new one. So you have the original state, you have your brand new list, and also while you're doing the first scan and storing the values in the set, you're able to, sometimes you'll want to do some extra processing like logging or calculating statistics or something else. So when you start diving into like more complex programs, that solution will be good for that sort of thing. But I won't even jump into that right now. I just want to give you a sneak peek of this. So feel free to challenge yourself and try to solve this one. Like I said, it's very similar to the iterative solution I showed you on the first day and the second day. It just has event space complexity. You're using an object to track. Yeah. Does anyone have any questions before we hop off?
So
No, I'm good.
So tomorrow we're gonna do the same problem, but we're gonna use sets, and that's it.
Yeah, so this is what I'm hoping. I'm hoping someone is able to solve this one that I just showed you. So the one with the set. And then if someone's able to solve that one and just like share their solution in the beginning of the event, then I'll go ahead and I'll jump right to the next one where you do like a full scan, store the values, and then do another iteration to like recreate another one. So so hope we might be able to get through 2. If no one's able to solve that one tomorrow, we'll do a walkthrough through that solution. Yeah, so the one that I just gave you a sneak peek of, we have the full scan, and then I have another method where you convert the linked list into an array. Use like splicing methods or just use like built-in methods to process it and remove duplicates, and then or even converting it into a set would probably be the best idea because it'll automatically remove the stuff as you convert it into a set. And then convert it back into a linked list. So that's the last one. There's 3 more solutions.
So I have a question. When it comes to sets, sets basically are like a data structure where you don't have duplicates, right?
Yep.
So the thing is, let's say that you have 2 nodes and both nodes have a value of 1. They have a value of 1. But the problem is that they're both objects, and objects are different in memory, even though they have the same value. So how would the set go about differentiating between the two? Like, does it have to go like to the using the value to do that? Because otherwise it's just different spaces in memory. How would it know like these are two different references? You get what I mean?
Yeah, so you'd be pointing to the actual value, not the
Okay.
reference. Yeah.
So you maybe like you store the values in the set, and then you recreate the linked list with the values that you have there in the set, right?
Yeah, exactly. Like iterate over the linked list by just doing like while current is not null, current equals current dot next, and while you're doing that, just checking if the current value is in the set. If it is already in the set, just skip. Just
Yeah,
move to the
yeah.
if it's not, then
The
add
next
it to
one.
the set and then still just skip, move on.
Yeah, I forgot what it is with the set. Like, it's something like get or something like that. I don't know what the method is to check the if it's inside the set. But anyway,
It's just
okay.
has.
Yeah,
Yeah.
it has add delete, right?
Yeah,
Okay,
super simple.
I think I can already make sense in my mind how to do it,
Cool, cool.
but don't test me now.
Yeah, nah. If one of you guys solve it, then I'm interested in seeing your solution tomorrow before we even get started. Before I go over anything.
Okay, sure.
And if not, I'll break that
So
down in much more detail.
so also Friday we're not doing algorithms like we're doing the project event, right?
Yeah, Friday we're doing demo days. People are sharing their projects. So obviously, y'all who have the trials and the memberships are going to be able to go first. So even if you have a small project, it doesn't matter. Just share it. Get the feedback. You're going to get improvements.
Mhm.
You're going to get advice on how to go about development. It's going to be really good. I do have a project I want to share as well. I'm building a forum for the O1 Software Network website, and so I would like to get feedback on that as well.
Awesome.
But yeah,
What are you using for the front end?
I'm doing server side React, so
Okay.
I'm serving React components from a Node server.
Okay, cool.
Yeah.
That's great. And also, I just got a notification that Tuesdays are going to be intermediate, right? And you're moving linked list to intermediate, if is that correct?
Yeah, so after this week, I'm going to keep the beginner's guide to data structures algorithms as arrays, queues, stacks, and strings.
Mm-hmm.
And then I'm gonna start next week. Actually, we're gonna start doing intermediate data structures and algorithms on Tuesdays and Thursdays from 6 to 8. So it's gonna be a longer event. We're gonna be working on stuff like more advanced array, stacks, queues, and string problems, and linked lists and binary search trees. So like introductory linked lists and binary search trees, and then in like a month and a half after I start adding some more like web development and just like project based like practical stuff, then I'll add more difficult stuff like just more intermediate binary search tree, linked list, introduction to graphs, priority queues, heaps, that sort of thing. So
Okay,
yeah,
that's fine.
cool.
Well, I'll attend the intermediate too, so it's fine.
Yeah. I had to make it a little bit longer because I realized that with this week of even just linked lists, like making sure you have a thorough understanding of it. It's like,
Hmm.
especially with linked lists, trees, graphs. These are things you really need visualizations for. It's hard to really help people wrap their head around it without visualizations. Like just doing it with code or
Yeah,
just explaining it, it's really challenging. So it's forcing me to
yeah,
step my game up too, which is nice.
that's awesome.
Yeah.
And yeah, like Jim said, if anyone has questions regarding how linked lists are structured, I can try to explain after after these events.
Cool. And yeah,
Anyone? I guess they all got it.
Nah, I'm good to go. I'm try to go back and watch the videos too, so I can kind of
Okay, sure.
up as much as possible.
Yeah,
Yeah.
totally.
Yeah, sure. There are plenty of tutorials online too. So
I was going to say I've seen a tutorial on kind of what we just gone through when I was kind of like studying like stuff that I needed to know for interviews.
Mhm.
So not to say I'm an expert in it, but you know, I did at least look at some things that it'd be nice to kind of do some problems in practice. Though I'll try to like solve them
yeah,
before the solution has, you know.
yeah. You're right.
See,
Sorry, go ahead.
no, I was about to say just kind of see what I can get from that. So
Yeah, because the thing is, on Monday, I knew how linked lists work on theory, but I
Yeah.
couldn't solve anything. Like, I would just freeze, you know? And now I'm able to kind of get around solving them. So it's absolutely, like, necessary to get your hands dirty. Otherwise, you're not really learning as much as you think you are.
yeah.
You get stuck in tutorial hell. So don't be afraid of trying and failing if you have to. Like, it's just one step to success. I know it's a cliche, but it's true.
I just posted a picture for everybody in the chat.
Yeah, that summarizes it.
Yeah, that's it right there. All right, cool. Yeah, if anyone has any questions or concerns after we sign off, feel free to reach out to me. Otherwise, I will see y'all tomorrow night. Enjoy the rest of your night, guys and gals.
Okay, thanks.
Have a good night.
See ya.
Okay.
Good night, guys.